All right. Well, welcome everyone. Let's make sure that our Zoom is working here. Uh, we did figure out how to close this down. There you go. All right, excellent. Yeah, welcome everyone. My name is Brian Jackson. I'm a professor here in physics, teach physics and astronomy. You are here at the monthly First Friday Astronomy Lecture Series that our department hosts. I don't know how most of you are regulars, but just in case you're not, these are a monthly lecture series that take place on the first Friday of every month, 7:30 p.m. Mountain Time, all throughout the calendar year. So we're not actually we're in summer session right now, but these take place all through the year, all the way through December, January. Sometimes folks are confused. They think, oh, it's a holiday, so they must not be. No, we're doing it every month. So if it's 7:30 on a Friday, on the first Friday of the month, this is a really great, like, cheap date. um, we do these lecture series. We bring in a space scientist or someone space science adjacent. They give us about an hour-long talk. We take questions, and then if the weather's clear, we'll go up to our on-campus observatory and do some stargazing. The weather is clear tonight. I have enough students to run it, so we're going to go up to the observatory. It's just maybe a 5-minute walk across campus to the west. So if you're interested in sticking around for stargazing after the lecture, go out to the lobby and hang out there. The students will be happy to take you over. I will caution you that the observatory is not ADA accessible, so you do need to be able to go up and down stairs, but it's only like 2 flights of stairs, so it's not that bad. But yeah, if you're interested in that, please stick around. We have a lot of nice telescopes to show you the night sky. It will probably run a little late. As you know, the sun doesn't set until like 5 in the morning in Boise in the summer. So it will probably start about 10:30, depending on what time the sun goes down. But that's an option. These programs are 100% state donation supported. We don't get any state support for these. We don't get any federal funding for these. If this is kind of programming you enjoy and want to see more of, feel free to visit boi.st/astronomy campaign. These letters have to be capitalized, I'm told, and you can make a donation to help support this program. Those donations pay to bring our speakers into town, pay for some pizza for our students, those kinds of things. Very simple things like that. Okay, and with that, I would like to introduce our speaker for tonight. Dr. Elizabeth Macdonald is a NASA civil servant who works remotely from Walla Walla, Washington, the other Washington. She got a bachelor's degree from the University of Washington, followed by a PhD from the University of New Hampshire. Not only does she work for NASA, she's also a science activation principal investigator. This is a big outreach grant program that NASA runs, and so you're going to hear a little bit about that program, I think, tonight, in addition to some really great other science having to do with the Aurora. So with that, let's welcome Dr. Elizabeth Macdonald.
Hello, good evening. Hopefully, welcome to everyone here and online. Hopefully, you can all hear me. And thank you so much for coming out on July 5th after the usual fireworks. We have a different kind of fireworks for you here today. And I'm excited to talk to you about Aurora, which is my specialty, and a citizen science project that people can participate, anyone can participate in, called Aurorasaurus. That's my project. Let's see. So we're actually going to talk about a bunch of different stuff today because we are having a very big year with all kinds of activity. So we'll talk a little bit about what is heliophysics and this big year that we are having, things that you've heard about, helio what, some of you might be saying. And then we'll also talk about public participation in science and some of the open science questions. A little bit about me first. So I am not the person that took the beautiful Aurora photos that were time-lapse that was playing before the talk. That was a professional photographer up in Calgary. I'm just a very amateur Aurora hunter and photographer, but I have worked on instruments that have flown in space that actually count the particles that cause the aurora and where they're from. And I worked at Los Alamos National Lab doing that for about 10 years for both NASA and Department of Energy missions. And then I moved over to NASA Goddard in Maryland, and now I am in Walla Walla again. And I've also worked on rockets that are smaller, shorter experiments than satellites, but really good training opportunities for students. But when I was the age of some of you, I had no idea that this was what I would end up doing, and I wasn't that keen on physics when I first took it. And I was basically kind of weeded out until I got very fortunate and had a research job my first summer of college at the University of Washington. And I was introduced to this field that contains a lot of beautiful questions and interesting phenomena. So I have always known that many more people could go on and become physicists and contribute. And there's many ways that everybody can contribute, even if you don't want to also go through all those math classes and graduate school and all that too. So we'll talk about all that fun. But I'd also like to learn a little bit about you. So how many of you saw the aurora in May? Excellent, excellent, great. And how many of you were at the earlier First Friday talk right before that was about auroras? Any repeat customers? No, okay. I was going to say there are major updates since that talk from what just happened. So we're going to talk about all of that. Let's see. So have any of you ever done citizen science? Can you raise your hand? Awesome. Is there anybody here who's done Aurora citizen science? Don't be afraid. All right, you can still possibly, since you have photos, you can submit them. Yeah, you can.
Which mic do you have? Is it mic? Sorry, folks. Here's 1 second. Mic 2.
So you can still submit your photos from May because there's still a lot to explore. So also raise your hand if you love nature. Yay, a lot of people love nature. Raise your hand if you think helping with scientific research sounds fun. Excellent. Okay, you all are well equipped to become citizen scientists then. So we'll talk about different ways you can join in this fun through this talk. But to start with a few basics, so I just want to define this word of heliophysics, which is a special area of science at NASA. It's the study of the sun and all of its effects throughout the solar system. And then let's see, what is aurora to start with? So we're going to talk much more about this, but it's basically starts at the sun, and it's like the last step in a process that has many steps from the sun to the earth. Where we get particles from space raining down on the upper atmosphere and producing these lovely colors. But it happens on both sides of the Earth at the same time, aurora borealis and aurora australis. And it can even happen on some other planets that have magnetic fields that might be like Earth's, which is like a bar magnet, just a North Pole and a South Pole. Or maybe they have 4 poles or all kinds of different scenarios on other planets. Let's see. But we'll delve into the new updates here a little bit on the May 10th storm. So let me see. This is an image of the sun. And I'm supposed to be able to get my other... It's supposed to have the sunspot, the big sunspot going across the sun. But basically, you can see it move across. Sorry, I'm not a PC person. So we want to stay sharing. But okay. So yeah, you can see this sunspot right here, this big, huge, scary one. That is the one that caused all this aurora that we saw. And it got really complex and active and was well aligned with Earth to hit us, basically. But how does that happen? Okay, so a few days before, we can watch the sun and we can see that there were many They're called coronal mass ejections. Those are the particles that come after the solar flares, which might be a more common word. And this is an official warning, or not warning, but sort of synopsis from the Weather Service. And the NOAA actually has a branch that is the official source of space weather prediction for the nation. So they do not just our normal terrestrial weather, but also space weather. So yeah, so they warned here that they reached this extreme level during this storm. This is kind of a view looking down on the sun and the earth and these multiple CMEs that hit us. There's a model that predicted this. And they take care of some of the warning systems for critical infrastructure and power lines and other things that can be affected. And the last storm like this that hit the top of the scale was in October 2003. Some other good information here. This sunspot, the sun is so large, but this sunspot was actually 17 times bigger than Earth all the way across, so roughly. So very large. And it gave us not just one of those coronal mass ejections, but like a dozen, most of which were aimed at Earth. So in heliophysics, we are concerned with both these applied questions of how this space weather can affect our technologies, as well as kind of fundamental questions like what could the aurora be telling us about life on Earth or other planets. So there are a lot of there's a lot of research at the interface between space and Earth science and the atmosphere, as well as planetary science and further out to what's astrophysics. But how does this energy happen? This is a good little kind of cartoon view of something large coming out from the sun, and then it comes towards Earth, interacts with the Earth's magnetic field, which transfers that energy to within the Earth's magnetic field, which kind of stores it up and then releases it on the dark side of the Earth back towards the poles. So that's the simple version of how the aurora happens. And that happens all the time. And then when you get a really large event that the sun is at the center here, and this is a view that shows the emissions coming out. You can kind of faintly see, well, some of them are more than faint, but you can see these, they're called halos, and they come out from the sun. And we actually, both NASA and NOAA, study these, look at the sun. They estimate, how much is coming out and what's the speed, what's its direction. And then they input that into models. And they were running these models to see when this is going to happen. This happened, these emissions were like May 7th and 8th. And there were like 5 or 6 of them together in this that all they kind of ran into each other. They were sort of different speeds, and then they came out towards Earth and really hit Earth kind of straight on, and also with a lot of oomph. And we don't always know how that's going to happen because the sun is 93 million miles away. And one parameter that's really important is the sun is a magnetic star, and it's emitting all these charged particles, this material. And that actually has embedded magnetic field. It follows the magnetic field. And that kind of varies in direction. And so when it hits the Earth, sort of right on the front side, that direction really matters as far as how much those particles are going to be able to get within Earth's protective magnetic field and energize the aurora and things like that. So we don't really know that until particles have traveled a couple days and almost gotten here. And then we have a couple satellites that can see the strength of what's about to hit us and predict the aurora there. So then all those particles enter the magnetosphere. They swirl all around to the night side. They bounce around tied to these magnetic field lines. They get excited and jiggled, and some of them rain down on the upper atmosphere, where they actually go down to about 100 kilometers and produce light by impacting the particles in the upper atmosphere, exciting them. So this shows that there are different colors at different altitudes, and the particles rain down and they make a number of collisions. So they make all this different light as they rain down in altitude. And actually the oxygen that's up there, it's not like the air here that we breathe. It's not thick like this. There's just a few particles, mostly oxygen, nitrogen, a little bit of hydrogen and helium. And then they get excited, and depending on the density, which also varies with altitude, you get these different colors. But oxygen can make both red and green. And then the nitrogen also makes both blue and kind of this pink lower layer. And that's what it typically looks like. And this is what it looked like May 10th and 11th, which is quite a bit more exciting, colorful, rare, unusual, all these kinds of words. And these solar storms actually also cause GPS signals to lose lock in a way that affected people who were planting corn in Iowa. And so that was one real life space weather impact from this storm. There probably are a few others. And we've seen space weather have other impacts recently. For instance, a couple years, maybe just a year or two ago, there were some Starlink satellites that had just been launched, and they were launched kind of right between two very small storms that didn't cause anything like this, but very small storms of aurora and geomagnetic activity. And they did not achieve altitude. So, 40 of those $1 million satellites fell back to Earth that were ejected. And, space weather and its effects on technology change as technology changes. So we're now in solar maximum, and there's different technology now than there was 11 years ago when there was the first or the previous solar maximum. So for citizen science, this was really exciting to my project because this was like the culmination of a vision that I had like 10 years ago. And then we didn't have any huge storms, but we always see more activity, more reports when the aurora is going to come down into the mainland US and down to more populated areas than where it usually hangs out. But yeah, so we saw thousands of reports, more than 55 countries, all 7 continents. And it's really exciting because this is the first storm ever captured, first really large storm captured by digital cameras. Because the last one that was this size was way back in 2003. And in 2003, some people had digital cameras, but not the majority. So many more sensitive cameras, basically. And the cameras are more sensitive than our eyes. So cameras see color at night better than our eyes do. So there definitely was color. If you were in Boise proper, you probably didn't see it that much, but your camera picked up a lot more. Yeah. Okay, so the auroras also are important for indicating these essential ingredients for the aurora, that you have an atmosphere to bounce off of, and that you have a magnetic field to guide these particles down into. And both of those things are actually critical to life on Earth and, the oxygen that we know and love and breathe all the time. But there's also really open science questions. So there was all kinds of red aurora during this storm. Red aurora can happen in like 4 different ways during large storms. So people's reports of where and when they saw the red aurora are really useful to figure that out. And we're really delving into that now, but it's going to take some time. So yeah, but it's really exciting. I was really amazed by how good, like even my iPhone, not even the latest iPhone, but how good it was, and how the aurora was forming these structures that are, when the aurora looks like this, it's called a corona. And that is actually like a visual effect, because the aurora is happening so high up that it's kind of like looking down at the horizon. Like if you're looking down a railroad track that's going a long way to the horizon, those lines will seem to converge. Or if you're in a city, a real big city, and you're looking up at skyscrapers, you know, it'll look like it's converging above you. But in this case, there was just tons of color. And these coronas mean that the aurora was stretched out so much that the magnetic field was directly above us here in the Northwest. So that also means it was visible very, very far south, down into Mexico and the Caribbean. So lots of exciting reports. And we've also been having a very big year for heliophysics because the eclipses earlier this year. So I'm going to talk to you a little bit about that effort, which we've dubbed the heliophysics big year, including, you know, all the big eclipse activities. Did anybody here see the eclipse? Excellent, excellent, awesome. And we're going to continue celebrating with citizen science and our solar maximum and our missions as well. So this big year started in October, last October, on my birthday, which was the annular solar eclipse. So a very good birthday eclipse. And then continued, you know, kind of peaked here at the April solar eclipse. And then it's going to officially end for us in the end of this year with one of our flagship missions in heliophysics, called the Parker Solar Probe, is making its closest approach to the sun at the end of this year. And all of this is also going on while the sun is really close to its maximum, which happens every 11 years. You know, officially maximum is kind of the peak of that curve. And we can't really tell where the maximum is until we crest that curve. So we could be there now, we could be there in 6 months, something like that. The big year is NASA is celebrating with all kinds of activities, and a lot of these are like social media campaigns, so you can follow NASA Sun and see what they're sharing on different ways that the sun touches everything. This is kind of a cool video about the solar probe. Again, this is like a visualization, but it coming really close to the sun. I think within 4 solar radii, and measuring the particles that the sun is emitting, how it gets so hot. The outer atmosphere of the sun is really hot. We can't see that directly at any other time other than during the eclipses, which is why eclipses are so cool. One of the reasons. Pardon? No. Will it survive? Oh, yeah. Yeah, yeah. It's supposed to survive. Yes. Good question. This is not a Phoenix kind of Icarus kind of moment here. So yeah, it's orbiting around and then getting ever closer. So yeah, it's going to survive. We hope. It should be engineered to survive. One more question. Yes. The what? Oh yeah. Mm-hmm. Sure. Yeah. If you Google NASA and helio big year, you will come up with, and NASA sun on social media, and you will find that stuff. So a little bit about the eclipses, why eclipses are so fun, how there's been citizen science with eclipses. So I showed you some pictures of the sun before, and I didn't explain all of them, but often there's a gap around. So this is a composite image of different satellites looking at the sun in different wavelengths and in slightly different ways. And one of the ways that they look at the outer atmosphere of the sun, it's not so bright. So you have to block out the sun in order to study what's happening in the outer atmosphere, which is why you have some gaps, some regions that we can't reach with our instruments. These instruments that block out the central disk of the sun are called coronagraphs. And we can only get so close. So we can't actually see all of this exciting stuff right close to the sun where this activity really gets accelerated and launched. However, you can take those pictures during an eclipse. And so people are always studying eclipses, but an eclipse only lasts a couple of minutes from one location. And also, if you have a fancy telescope, you might not be on the path of that eclipse. And so there are actually several different citizen science projects that operated and were operated by people just like you. Maybe somebody here was involved in some of them during the eclipses to study the corona and its dynamics during that time. So if you take people all along the path, you can extend the time that you're able to observe the sun in great detail from like 5 minutes in one location to, I want to say it's like an hour and a half total, that the eclipse path would be observable from like land, basically, mostly. And of course, we were very interested in whether the sun was going to have one of these exciting coronal mass ejections during the eclipse. And it didn't quite happen. It was off by a month, you know? So in April, there wasn't one of those at the exact time. But a month later, there was. And in the historical record, there are examples of that as well. Yeah, so again, this is more of a movie of how we can observe this a different kind of corona. There's many different kinds of coronas here. Outer atmosphere of the sun, but not the super close part. So there are many open questions. One of the open questions about the sun is how that corona gets so hot and how what comes out from the sun is accelerated. It's actually hotter than the surface of the sun. It's 1,000,000 degrees and very, very hot. So shifting back to auroras, there are also many interesting questions. Does anybody know what this is? You will find out. Okay, there's kind of the normal aurora in the background here. And then this was taken from Canada. So about Calgary or Banff. And so with the naked eye, this sort of mauve structure looks mostly like an airplane contrail from east to west. But with the right cameras, you can capture so much more dynamics. And we worked with Canadians, both citizen scientists, and studied this phenomena. And the citizen scientists, we didn't know what this was. They called it Steve. And so this is the new aurora called Steve. And this is sort of a good quote about being a scientist that I like. And really everyone can do this. You know, if you see a photo, something like that, you capture something you don't understand. We can take more information, we can ask systematic questions and gather more information about it. And that's really what happened with the Steve story, which I will get to. But citizen science does work at scale with people collecting data, asking questions, interpreting results. And it can be very reliable, valid science outcomes, and a lot of unexpected discoveries, including like, what is that spider in your basement? That would be a project for the iNaturalist citizen science project. You can take a photo of that weird spider in your basement and upload it there. And they've really found new kinds of spiders. And you can also learn about what the local spiders are, or anything. Birds are another good example. So these are a couple of projects that I really like. I'm only an amateur birder, but iNaturalist works on mushrooms and flora and fauna, and it's fun, really fun. NASA also has a number of fun projects that can be done by anyone. Some of them can be done anywhere, so on your computer usually. And that's the website for the NASA citizen science projects. Many of them involve people looking through NASA data and helping find things. There's also a nice organization called SciStarter that you can filter and find a project. So if those two, if you're not into birds and you're not into galaxies, but you are into sourdough bread or something, you can put that on the search at SciStarter and you will find a citizen science project. I almost said beer, but I was like, no, it's actually sourdough. Yeah. Here are a bunch of projects with the heliophysics big year. And the ones that were involving the eclipse are at the top here. I'm not going to take you through all of them, but we did have 4 different projects on the top row there where people observed that corona with different kinds of technology, different types of telescopes, some people just with their cameras, and some people even just with their cell phones. And there are some really cool science applications, even with just a really coarse image of the sun that we'll be looking at. And then there's a few projects that studied the environment and the soundscape. There's one project called GLOBE, which is an earth science, environmental science project, has a ton of teacher resources. That one can be done anytime. In the case of the eclipse, people were looking at temperature changes and cloud changes and something else, maybe, I forget what, but really cool stuff there. And then there's a couple projects involving other radio effects, if you might be a ham radio operator, or there's a project called Radio Jove, which is a way that you could have a telescope antenna in your backyard looking at the sun, Jupiter, and changes in the upper atmosphere. So if any of you, maybe not in a city environment, but have a nice rural place to host a radio telescope, Radio Jove would be a great project. There's also was a project involving a bunch of students called the Eclipse Ballooning Project that was led out of Montana. And they had student teams from all across the country studying the weather changes associated with an eclipse, which is really cool. And then there's a bunch of other projects involving the sun and eclipses that you can do from anywhere. That's this set of projects. And then there's some that involve going outside, and I will highlight those in just a second because you can still do those as well. Here's a few of the snapshots. You can see, in this case, this is a little audio recorder that people were recording changes in the biology and sound around them during the eclipse. And then this is one of the telescope setups that different teams received and trained for with the Dynamic Eclipse Broadcast Initiative. And this is a group of ham radio folks who were really excited to see how an eclipse, which is like a high-speed kind of sunset changing, the upper atmosphere, how that actually changes the transmission of radio waves. Because we know, some of you remember like AM radio transmits farther at night. That's because the actual levels and height of the atmosphere changes. And so the eclipse is a great experiment for them to study. And then, of course, they're also looking for how that atmosphere changed. There were some predictions about how that was going to change, which were really up to date with like all the satellite imagery of the sun. They tried to predict what the eclipse would look like, and then we're going to compare it to what people actually monitored all across the path. That research is not done yet either, because it just happened in May or April, excuse me. So yeah, but there's also these prominences were really cool to see, and the chromosphere of the sun. So different projects looking with different wavelengths and technologies. Here's a few more projects you might be interested in. So my project, Aurorasaurus, which I am going to talk a little bit more about, tracking auroras, submitting your reports. There's a project that some folks here are already working on called Exoplanet Watch, where you could observe exoplanets, find exoplanets using your own telescope or a remotely operated telescope. Which is kind of cool because you could be at home and then using somebody else's telescope. There's a project called Spraytacular, imaging these really crazy light phenomena that happen way above thunderstorms, right at the edge of space, right below where the aurora occurs. And then there's an upcoming project called EasyMag, which is your own kit to measure the Earth's magnetic field and changes in it due to space weather. Lots of little wiggles that happen, and you can actually see if aurora was going to be happening, it would change the response there. And that is a collaboration with a satellite mission and high school teams too. Okay, so auroras. There's actually some folks who see auroras a lot, and even back in 2021, which was not a very active year, Kevin saw all these auroras outside in Twisp, Washington, which is pretty far north. But what did people notice? Why was he such a successful aurora chaser? Any theories or things that you notice about this collection of pictures? Yep.
Because it seems like he did it at the same spot every time.
Yeah, he actually lived nearby where you just have to go outside and you have a nice view to the north. So that's really helpful because many of us, definitely myself included, are not quite as dedicated or have enough time to go out and chase it. He also knew when it was likely to happen. So he's watching the data, watching some apps. You can sign up for an alert on our website. And then also just, it varies a lot throughout the year. You can see, the background is quite different, and all the aurora constantly varies. So that's one of the reasons why people get addicted to chasing it, is that you never know what you're going to get. There are many different types of aurora. So the usual type, especially from Alaska, is kind of these discrete arcs that you see. Those look like curtains, and they can move over the sky. They can also swirl around and break up. You can also see when the aurora comes down to low latitudes, it's often more of just a little bit of glow. Or if it's a really large storm, it could be some of this really red glow, but not moving that much. There's also another kind that is not usually that bright, but has these pulsations. There was a little bit of pulsations. Maybe some people saw that during this storm, but only probably if you were up at like 2 in the morning, because these happen on the morning side of Earth, where there's actually different kinds of electromagnetic waves, and they cause these things to pulsate on and off, and they only get generated when our location on Earth rotates under the aurora, and it's like early in the morning. And then there's Steve, which tends to look like this, kind of mauve, and then a little bit of these green fingers. And we'll talk a little more about Steve. But here's how you can see the aurora, maximize your chance. You could go up north, further north, when it's dark. So don't go to Alaska in the summertime, but you also generally want to have as good of a view towards the poles as you can get. So you might be thinking about that for the next time here if you were to get an alert and wanted to go out of the city. Where can you go north and really see the northern horizon? Well, watching space weather forecasts, normal weather forecasts, and local aurora chaser groups. There's a bunch of those on Facebook. I am not sure about the Idaho groups actually, but there probably are. So that would be great to know more about. And yeah, it can take a bunch of different tries. And then also, like, we just had this huge event, so it's not likely to be that huge again, but you never know. It is possible for sure. And the aurora is, as I said, kind of quite a bit fainter to different people's eyes. It also varies by person. We have at Aurorasaurus, we do a number of things. So we have a newsletter. If you sign up for an alert, tells you about what we're doing. We also have some blog posts. We also have information on the Learn part of our website about the aurora. If I said something and you want to go back and check it out more, this was one of our recent blog posts that was very popular. Our project manager knit this great hat, which actually has the heights of the aurora scientifically accurate per knitting row. And you can see like how high up the aurora happens. You know, it's 100 kilometers, which is 60 miles, is this bottom of the aurora, pretty much where the green starts. And Mount Everest is down here at row 1. And any commercial aircraft is way down here at row 1. So yeah, it's very hard to reach these areas of space to actually sample them. And then the space station is all the way up here. Yeah. So next time, if you need a project, that is one of our more recent blog posts. Okay, now I'm going to tell you a little bit about Steve. People were out observing the aurora, and they started noticing something that was overhead as well when they were seeing the aurora far to the northern regions. It was unlike most aurora. Talked to the scientists, we didn't know what it was, and together they said, we'll keep taking observations, and we'll call it Steve in the meantime. Steve is mostly a very narrow purple arc, and sometimes it has these little green features that go along with it as well that are kind of like waving fingers or a fence. That means that there's plasma physics happening up there to cause that light and to make these little discrete features that we don't understand yet. We now have some satellite observations from the ESA satellite called SWARM that show that Steve optically is associated with a very strong flow in the particles in the ionosphere, the upper level of our atmosphere. Steve is important for a number of reasons. It's really exciting that people armed with cameras all over the globe can capture something that we didn't fully understand and shed new light on that. It's also really exciting that this happens further to the south where there are more people. So it might be a kind of aurora that more people can see than the usual kind. We're now able to look up at the sky and see things about the aurora and this subauroral region that we never understood before. And then we can correlate that with our traditional observations and lead to greater understanding. Some more views of Steve here. You can see it looks quite different from many different viewpoints. Aurora and Steve are tricky like that. And it wasn't seen in May, so we don't know why. But we do actually know that Steve is not totally new, which is like comforting. But we did miss it in previous reviews of the literature when we were trying to figure out what this was. And the reason we missed it is because it was further back than we typically look, which is 100 years ago. There were people, Carl Stormer was a scientist in Norway who had basically a citizen science network across Norway, and actually took some of the first photographs of aurora and the first kind of catalogs of many different types of aurora. And so he had a few events like this, and he called them feeble homogeneous arcs of great altitude. And really, to the extent to which he was able to study it, he studied it a lot. He did not have any satellite observations, though, but you can see some similarity in the photos. So pretty cool. And that was actually brought to our attention by a citizen scientist from Germany that we then worked on this paper with. So how does Aurorasaurus work? You can get a free account, and we send you emails when the aurora might be visible near you, and monthly newsletters. You can opt out of all of that. You can report your location and time when you saw the aurora. That's the basic in agreement that we can use these observations for research. That's the minimum information we need. We do need to know the location and time, at least roughly, but hopefully well. You can set your cameras to make sure the times are correct. You can check it out when aurora might be occurring on the website. We have some space weather data, one simple plot that you can check out, one model of where the aurora would be overhead, as well as this little red line, which is where the aurora could be viewed to the horizon. And this little red line actually, probably can't see it too well, but it bumps out when people might be seeing it even further south than is expected, because the models aren't that well behaved and we don't know exactly what happens during all these big storms. And so we built this into our system that it would adapt and make other alerts if people, no matter where, like a cluster of people around you might be reporting aurora. So you can help others, and that actually generated some alerts in Texas and Alabama during this storm that we never would have thought. And then we also have, education resources. Here's where our reports came in from across the US. And you can see Idaho is pretty well represented here. Not as well represented as Washington, which probably reflects that I have not been here and, been online and generated that much networking here. So we'll work on that today. But yeah, so it's a great time to be a heliophysicist, and we would love for you to join us and submit reports and ask questions. And that's the end of my talk. Thank you. All right, I know some people have questions. Yes.
Oh, I was just gonna ask you, where you need all these amateur people to help you along an eclipse line,
Yeah.
and you say that, it could travel across our country in a matter of hours.
Yeah.
Or whatever like that. I was wondering, if you guys can't find a budget where you could put something on a jet and go along the line.
That is also done, yeah, but you can't put everything on the chat as well. Yeah, so that has been done also. And last time I gave this talk, a young man told me how that was done in the 70s with the Concorde and got the longest observations there. So, but NASA had some research jets and they also had some instrumentation. And I should have a better answer for you of how that's a little bit different, but I can look it up. Yeah. That's actually with the project called Citizen Kate. The person who led that project also led the research on the WB-57, which is the NASA plane. So that would be the place to look, Citizen Kate.
And so I also had a question, the heliophysicist. And so you study the effects of the sunspots and the sunburst and all that stuff on our climate and how it affects our temperature on Earth and all that.
Yeah, that's a very good question.
I think you should repeat the question for folks.
Yeah. Oh, sorry. Great question. The question was about how heliophysics may, do we study it with respect to the Earth's weather too? And so the Earth's weather, as you saw in that little, most of the Earth's weather is way, way, way below where the aurora happens. And the sun's activity, even though it varies and its output varies a little bit on the 11-year cycle, that doesn't change significantly the weather. Might be 0.1 or 0.1%. There's a teeny tiny change, but not a large change. And then it's starting to be studied from, connecting how atmospheric conditions go all the way up to space. But it's kind of like the range, like the first climate models didn't go that high up in altitude. And then the Aurora models didn't go that low. So that's an open research area, but there's not a huge amount of coupling there. Yeah. More questions? No dumb questions. Yes, possibly in the back.
You're watching it back in May.
Yeah.
The kind of like the way I described it is like when a piece of metal gets like a piece of hot metal gets in, there's that like white strike effect. We saw a version of it like atmospheric. What causes that? It doesn't quite look like the other.
Yeah, I don't know what you saw. Yeah, maybe it was the pulsations. There were a few minutes and I wasn't too far away from here. So like I was staring up, I mean, so much was happening all across the sky that you could be watching something over here and you missed what was happening over there. And it was just really exciting. But there were a few minutes late in the night and other times where it was like flickering really fast. So it can be pulsating. Pulsations are usually like a couple of seconds. And then there's another kind that's called more flickering and it flickers really quite a bit faster. So yeah. Okay.
Up with the southern hemisphere, you didn't talk about that at all.
Yeah, so the Southern Hemisphere aurora, there are aurora chasers. We collaborate with those folks and some of their groups, their enthusiast groups. There aren't as many land mass areas to observe the aurora from in the Southern Hemisphere, so not that many people can see it. During this storm, it was seen in South Africa and the southern tip of South America, which is extremely rare. And it was seen pretty much throughout Australia and New Zealand. But there's a lot of groups in Tasmania, New Zealand, and southern Australia that do regularly chase aurora. And yeah, those observations are also like, you want to look and see if it's asymmetric, but that's a little hard to do just from the optical, because you're not really lined up. Those field lines, magnetic field lines, they intersect the Earth at points in the northern and some southern hemisphere, but it's really hard to get cameras or eyes on both of those points at the same time. Yeah. But they see Steve down there. Yeah. More questions? Yes. Yes, sorry. All right. What was that research? Oh, I think it was the Easy Mag project, which they're gearing up right now. They've got, they're kind of in beta launch right now, and I actually have one of their magnetometers. I should have brought it. It's at my house. But they're looking for partners in high schools to host these magnetometers, and you upload the data, and it's a pretty cool small kit. We normally take like citizen science, like there's science grade instruments, and those instruments are like buried underground, and they're thousands of dollars, and they're professionally calibrated and all that kind of stuff. These are not, but if we have many more of them, what can we learn together from those? There are different ways of doing that, and also the cost for some of the components has come down a lot. Yeah. So I can write that down, and I have some cards, and if people want to come up, I have a few cards and brochures and stuff like that. So any final question? Diehard folks here? Yes.
Does it look different from things looking towards the Earth?
Yeah, it does. And let me see if I can go back. Whoops. You can see the height of it from space. You can find some cool movies online of this from the International Space Station. Actually, the astronauts take photos, and sometimes there's some cameras. This is one photo of it from space. That's quite cool. But typically, it's the astronauts actually taking photos, and they don't always, they have very busy lives up there, so they don't take all the photos of the aurora all the time. And then the inclination of the space station actually doesn't get to the latitude of aurora that often, so they don't see it all the time. And one more, last question.
What is the risk? What's the physics there that says
All right. Yeah. So the question was, what is the power grid risk, and what's the physics of that? So I'll start with the physics, because the aurora is charged particles raining down electrons. And so it's like a current. There are many currents, and it induces currents in long conductors on the ground or other sensitive components. So it can induce currents in places on the ground. That can vary by the rock in the ground as well. And there was a large power outage and costly power outage in 1989 from Quebec that was like a 9-hour power outage, and transformers and a couple of, some significant things got damaged. But since then, there's been quite a bit of protection, education. They pay attention to this more so now. So not to say that there is no risk, because it's still something that we watch and track and all of that. But, people are happy that this last storm did not have any significant damage in that area. Yeah. Whoops. All right. Great. Thank you all for the great questions.
Well, thanks for coming, folks, and come back in August. We are going to have Dr. Jason Williams from NASA JPL's Cold Lab come and talk about his work on cold atoms. And be sure to grab a flyer for our November event. Those of you who don't know, we're going to have Dr. John Mather, 2006 Nobel Prize winner in physics, come to speak to us on the 1st. He was also the scientist who kind of rescued James Webb Space Telescope. So we have flyers for that event out here in the lobby. Yeah, he's super nice. So I think it'll be a really excellent talk. So that'll be November 1st. Great. See you in August.